All right, moving on to our last section, 7.5. We'll look at solving trigonometric equations. So we've been working with identities in this chapter, and we're going to use some of those properties in helping us. But remember, an identity is an equation that's true no matter what you plug into the variable. Now, a trigonometric equation, right, not an identity, right, is an equation that's true for certain values for that variable, assuming it has a solution. So again, we're not talking about identities, where it doesn't matter what you plug in the variable, it's going to be equal. We're looking at equations in which certain values will satisfy the statement. So with solving these, we're going to be using a lot of algebraic properties, a lot of algebra review in helping us. And we might need to refer back to some of our identities on some of our problems. And of course, applications of our trigonometric functions and their definitions. We'll be reviewing a lot that we've already talked about this semester. We're finding the values. Now, let's solve, of course, by hand. We can always check if we wanted to with our calculator graphically, but we want to be able to solve by hand without relying on a calculator. So let's start with this first equation. Start basic. So solve finding all solutions. Express solutions in both radians and degrees. So we'll give it in both forms. So looking at our equation, all right, let's go ahead and look at solving it. Now with 2 cosine x equal -1. Now we want to solve that, right? What we want to do is we want to get x by itself, right? In an equation, you could think of this trig equation like a linear equation. If you took out the cosine function name, it would read 2x equal -1, right? We would solve by dividing out the 2 on both sides, and we would have x. Well, same process. I want to solve for x. I want to get that cosine x term by itself. So my first step, right, would be to get rid of the coefficient. Let's go ahead and divide out the 2 on both sides. And as we do that, right, it simplifies down to the cosine of x equaling -1/2. Well, now we've got our x term by itself. We've got our cosine function of x equal -1/2. Well, we should be able to solve this. We should be able to recognize the solutions. We don't need a calculator, right? We could find x by using inverse properties, right? X is equal to cosine inverse of -1/2, but we should recognize -1/2, right, is one of our special angle values, right? So think about with cosine. We want cosine, right, by referring to the x-coordinate. We know cosine, let's use our unit circle approach, right? So think about on a unit circle, when would you have an x-coordinate of -1/2? Well, we have an x-coordinate of 1/2 at our 60-degree or pi/3 rotation on the unit circle. So with negative, we're going to need to be in quadrants 2 and 3 because x-coordinates are negative in quadrants 2 and 3. So let's talk about our 60-degree mark in quad 2, which is, 120 degrees, 180 minus 60, or pi minus pi/3, which is 2 pi/3. So let's write that down. And if you need to refer back to unit circle, you can. So 2 pi/3 or 120 degrees, right? We have a ordered pair that reads -1/2 square root of 3/2. And there's that x-coordinate, right? The x-coordinate, right, is -1/2. So that implies, right? So we're talking about function value of -1/2. We know the cosine of 2 pi/3 or 120 degrees would equal -1/2. So there's a solution. So down here, we begin writing our solution set. So x can equal 2 pi/3. Now, that's one solution, right? That's one angle measure in quad 2. There's infinite angle measures that represent that same ordered pair of -1/2 square root of 3/2, right, by using coterminal characteristics, right? We can add or subtract any multiples of 2 pi, or 360, and we'll get back to that same ordered pair. We get back to that same function value of -1/2 for cosine. So to take care of that, all right, 2 pi/3 plus any coterminal angle. So what I want to look at, all right, is including those. So we're going to add what we call 2k pi. All right, plus 2k pi. Now 2k pi, now I'm going to let k represent your integer set. And in math, we abbreviate integer sets with our capital Z. I'll write that here beside it. Integers. So 2 pi 3 plus 2k pi. So for example, if we could let k, what is the integer value? Right? 1, -1, 2, -2. So if we're looking at, for example, k being 1, that integer value, we would have 2 pi. 2 pi over 3 plus 2 pi, right, would be what? 8 pi over 3. 8 pi over 3 is coterminal with 2 pi over 3. It's in the same spot. That would be a solution. Or we could subtract 2 pi. We could subtract 4 pi. We could add 4 pi, 8 pi, any multiple of 2 pi. So k takes care of those multiples. Of course, that's in radians. Or if we were writing it in degrees, we got 120 degrees plus any multiple of 360. So k times 360 degrees, where k again represents an integer. So that takes care of all the coterminal angles, all the quadrant 2 6-degree angles. Now let's go back to the unit circle. All right, we also have on the unit circle, right, we can think about quadrant 3 in our 60-degree mark, which is 180 plus 60, which is 240, or in radians, pi plus pi over 3, which we know is 4 pi over 3. So 4 pi over 3 radians. And again, if you need to get out your unit circle, you can. And again, this is 240 degrees. We're writing it in degrees. 180 plus 60. We have an ordered pair of -1/2 square root of 3 halves. Or actually negative square root of 3 halves. In quad 3. But there's that x coordinate, right, of -1/2. So with that said, we know we were asked to find the value of the cosine of 4 pi over 3. Right? Our answer would be -1/2. So there's a solution, right? -1/2. So that's what we're looking for. So another solution would be, right, also x equal to 4 pi over 3 plus any multiple of 2 pi, so 2k pi. Or in degrees, 240 degrees, plus any multiple of 360 degrees, right? Full circle. So we'll be right back at the same spot. So there's our solution set, right? As we're looking at the solutions to this trigonometric equation, and that's taking care of every possible solution, right? Now, with that said, let's move on. Let's go to our next example, here number 4, or page 4. Let's look at solving. Let's look at solving this one. So find all solutions, plus solutions both radians and degrees. Let's take example A first. We got the sine of x plus the square root of 2 equal to negative sine x. Now, my first step, I've got multiple terms, a little different than our last one. Got a couple of sine x terms. My first step, we want to get the x terms together, right? We want to solve for x. So let's get these sine function terms together. So I'm going to add that over. And while I'm at it, I want to isolate it. So I'm going to move this square root of 2 to the other side. So to do that, again, let's show our work. All right, let's go ahead and add that sine x to both sides of the equation. Use the addition property of equality. And then let's do the same thing with square root of 2 to move it to the right side so we can isolate the sine x terms. Let's subtract square root of 2 over. And as we do that, we now have what? The sine of x plus sine of x, which is 2 sine of x, equal to the value of negative square root of 2 after we subtract the square root of 2 over. And then we're close. We want to get x by itself. So again, I'm thinking of it just like I would a linear equation, right? Just like it would read 2x equal negative square root of 2. Let's go ahead and divide out that 2. Both sides, so we can isolate. And as we do that, we have the sine of x equal to negative square root of 2. Well, again, we can find our solutions now, right? We should be able to recognize this as one of our special angles again. So again, thinking back, if you need to, using the unit circle approach, with sine, we know we're looking for y coordinates, right? Sine's evaluated by y coordinate, cosine's evaluated by x coordinate, tangent's y over x. So as we're thinking back to our unit circle, we go back to a y coordinate being negative square root of 2. We're going to be looking at the 45-degree marks in quadrants 3 and quadrants 4, right? In quadrants 3 and 4, we'll get same values of negative square root of 2. Now, let's go to quadrant 3. What's the 45-degree mark? 180 plus 45 is 225 degrees, or pi plus pi over 4 is 5 pi over 4. So I'm going to write down that order pair. So 5 pi over 4 radians, or 225 degrees. In quad 3, our order pair reads negative square root of 2, negative square root of 2. Right? And again, if you need to refer to unit circle, you have that, right? Here's that radian measure, 5 pi over 4. There's that y coordinate, negative square root of 2. Right? And again, degrees is 225. And you can also see the 45-degree mark in quad 4, right, which is 2 pi minus pi over 4, which is 7 pi over 4, or 360 minus 45, which is 315. What do you see with the y coordinate? So that's what we're looking for. Quadrants 1 and 2, the y coordinates are positive, so it wouldn't give us a solution. So again, if you need to, you can refer to unit circle. But again, we don't need a calculator. We don't need the inverse feature to find our solution. We can find it just looking at our special angles. So again, there's that y coordinate, right, that we were looking for. So that implies the sine, right, of 5 pi over 4 radians is equal to negative square root of 2. So there's a solution. So that implies x can equal 5 pi over 4 radians, right? And then adding all the coterminal angles plus 2k pi any multiple 2 pi, or if we're in degrees, 225 degrees plus any multiple of 360. 360 degrees. Now again, it's not all of them. We also have, right, 7 pi over 4 if we're on the unit circle, or 315 degrees, right? We have the order pair of square root of 2, negative square root of 2. But there's that y coordinate that we're looking for, right? We want the y coordinate to be negative square root of 2. So again, if I'm looking at evaluating, if I say what's the sine of 7 pi over 4, you would tell me negative square root of 2. So there's a solution. So we also have x equal to 7 pi over 4 plus 2k pi, or again in degrees, 315 degrees plus k times 360 degrees. So there's our solution set. We just solved this trigonometric equation. We found all possible replacements for x. Right? There's our values, all right, that would satisfy that. And you could check it, all right, if you were in your calculator, right? You could even go to your TI to check that quickly. Now, I mentioned checking these on the grapher. All right, if you wanted an easy way to check, would to be using your 0 command, right, on your calculator, or your intersection command. So you want to check, let's just, since we haven't checked one graphically, all right, this might be a good place to do so. All right, let's check graphically. So with that, I've got the sine of x plus square root of 2 equal to negative sine x. All right, well, let's use the 0 method. So applying the 0 method, all right, we set equal to 0 and graph it, find the zeros. So that means we would add the sine x over, right? So that would imply the sine of x, right, plus the sine of x. You can move it over to the other side to set it equal 0. So that would give us 2 sine x plus square root of 2 equals 0. And then we could graph that, right? We could put that in our TI. We could store that in y1, for example, and look for zeros. Now remember, on your TI, right, we can use radians or degrees. Let's go to our calculator. Let's look at 2 sine x plus the square root of 2. All right, on here. We'll pull it up real quick. So let's clear out our last one. Clear these. So 2 sine x, all right, plus the square root of 2. And at our mode, it's in degrees. That's fine. Let's go with a zoom. Hit your zoom button. Zoom 7 to a trig window, right? And you can graph in these. So go to your window real quick. Right now my window is in basically radians. Let's change that. So negative 360, negative 360 degrees to 360, 360. And we can leave that. But there's a graph of your function, right? 2 sine x plus square root of 2. Now you can see your zeros. Right? Let's look between 0 and 360, which you can see on the right-hand side of this y-axis. You see a couple intersection points, but how would you find those? Hit second button in Calc, and Command 2 is your 0 command. So you see it asks you a question to get a left bound. So I'm going to take my cursor. Remember, 0 is where it crosses the x-axis. So you can see my cursor moving here on my graph. All right, a little line there. And it says at the top of my calculator, down at the bottom on yours, it says, what does this say, left bound? That's to the left, 0. It's left of that x-intercept. Hit enter, and mark that location with an arrow on yours. And then slide down below the x-axis, and you'd be to the right of it. See the question says right bound at the top of my calculator. She's at the bottom on yours. Hit enter. And there's your 0, right? What does it say for x? It says 225. Well, that was one of our solutions, 225 degrees. All right, just go find the other one. Let's do the same thing. There's one more between 0 and 360. Here's a left bound. As you see, I moved my cursor. Here's a right bound. And here it says 314.99, which is 315. 315 degrees, which is 7 power 4 radians. I'm in degrees. Of course, there's infinite. As you can see, this graph, this wave repeats, and it goes on forever. And you've got those coterminal angles. You keep adding, subtracting multiples of 360, you're going to get all these zeros, all right, from this graph here. But that's what I mean by checking graphically, right? I confirm what we just did by hand. We don't need our calculator, but it's nice sometimes to check our work that way. All right, let's move on. Let's go to the next example here in B. Let's see what happens in this one. All right, so we got 3 tan squared x minus 1 equal to 0. All right, let's solve B. I'll put it down here. All right, let's put it down here at the bottom right. So with that one, 3 tan squared x minus 1 equals 0. Now solving that, again, I'm looking at only one x term. Let's just go ahead and isolate it. Let's go ahead and add the 1 over to the other side of the equation. And as we do that, we get 3 tan squared x equal to 1. And then we can divide out our coefficient of 3. Right? Get the tan x term by itself. And as we do that, we now have tan squared x, right, equal to 1/3. And then I want tangent, not tan squared. I'm solving for x. So our next step, since we've isolated, think of this as a quadratic, we've isolated the x squared term. We can take the square root, right, to get to x. So let's use the principal roots. And let's take the square root. Now don't forget, it can be plus or minus, positive or negative. And take that on both sides. And as we do that, we get the tangent of x equal to plus or minus the square root of 1 over the square root of 3. Which, let's go ahead and rationalize that. That's the tan of x equal to plus or minus 1 over the square root of 3. And you should recognize, of course, you can rationalize that if you like, right? We multiply numerator and denominator by square root of 3. What do we get? We get tan of x equal to plus or minus square root of 3 over 3. And that is one of our special angles with tangent. Hopefully by now, and remember, we're looking at with tangent y coordinate divided by x coordinate. And hopefully you remember from the unit circle, that takes place at your 30-degree marks. So on the unit circle, right, we're looking at ordered pairs. For example, if you go to pi over 6, right, or 30 degrees, we have an ordered pair of square root of 3 over 2, 1/2. Well, with that, if you take a tangent, I'll write it here above it, the tangent of pi over 6 would equal 1/2 divided by square root of 3 over 2, which equals 1/2 times 2 over square root of 3, which is equal to what? 1 over square root of 3, which rationalize square root of 3 over 3. So yeah, there's a solution. So we want square root of 3 over 3. So there's one of our answers. So x, we can go ahead and write that in. So x going to equal pi over 6. Here's the quadrant 1. And let's take care of the coterminals, 2k pi. So adding 2k pi to it, all multiples of 2 pi gives you all coterminal angles there in quad 1. Just remember k represents your integer values, k being an integer set. That's quadrant 1. Now again, you can write that in degrees, right, if you wanted. That would be also 30 degrees plus k times 360, all multiples of 360 degrees. So again, that's looking at only one quadrant right now. That's looking at, right, quadrant 1. Now, what's the 30-degree mark in quad 2? So 30-degree mark in quad 2, you're looking at what? 5 pi over 6. So we can look at 5 pi over 6, which is pi minus pi over 6. And with 5 pi over 6, right, of course, in degrees, 180 minus 30 is 150. There's your 30-degree mark. We would have an ordered pair of what? Negative square root of 3 over 2, 1/2. And yeah, if you find the tangent of that, right, that gives you a tangent value of negative square root of 3 over 3. And remember, we can be plus or minus. So we also have a solution at 5 pi over 6. There we get a negative square root of 3 value, right, if we would divide the y and x coordinates. So again, let's go ahead and write down those coterminal angles, plus 2k pi, or again, in degrees, 150 degrees, plus the multiples of 360. All right. And now let's go to our last two quadrants, quadrant 3 and 4. If you were in quadrant 3, what's the 30-degree mark? 180 plus 30 is 210, or pi plus pi over 6. That is 7 pi over 6. So that's 7 pi over 6. Right? Or, in degrees, again, 210 degrees. You have an ordered pair of square root of 3 over 2, negative 1/2. And if you divide those, what's negative 1/2 divided by square root of 3 halves? Tangent value would give you negative square root of 3 over 3. So again, tangent there in quad 3. Now this should be a negative, right? 7 pi over 6. Be a positive square root of 3 over 3, but as a solution, because remember, we can be plus or minus, positive or negative, where we took that even root of both sides. Tangent, yeah, in quad 3 is positive. Both coordinates there are negative. But with that said, that's a solution, so we got to include that. So we got the solution set of x equal to 7 pi over 6 plus the coterminal angles, 2k pi, or again, in degrees, right? If you want to put it in degrees, that's 210 degrees, plus those multiples of 360. And to finish it off, quad 4, 30-degree mark, 360 minus 30, 330. Pi, well, now we're at 2 pi. 2 pi minus pi over 6. That's 11 pi over 6. So 11 pi over 6, or in degrees, 330 degrees. We have an ordered pair that reads square root of 3 over 2, negative 1/2. And that gives that tangent value. So we have our last solution, x equal 11 pi over 6 plus 2k pi, or in degrees, 330 degrees plus k times 360. But there are our solutions. So we've solved, right? We found x, right? There's our solution set for this problem. So there are our solutions, right? All of them that satisfy this trigonometric equation. They're the values of x, right, to satisfy this equation. So solving these, again, that one, just isolating and taking the root. So algebraic review, a lot of algebra in these problems. We haven't needed a calculator. All of them involve special angles so far. We haven't needed a calculator to find out what x is. We've been able to find these pretty straightforward with our special angles. Moving on, let's go to our next page here. Let's find the solutions. Now this time, a little different. It says in the interval of 0, so find all x values greater than or equal to 0 and less than 2 pi. So we got some restrictions on our solution set. So let's go ahead and solve for x. Let's take this first example. So let's take example A. I've got the cotangent of x times the cosine squared x equals 2 cotan x. So we got a couple different trig functions being used in this one, a little different we've done. But I've got several x terms. So my first step, step 1, is let's go ahead and set it equal to 0. Let's use the 0 method. Let's set it equal to 0 and then try to factor. So that implies, well, to do that, we need to go ahead and subtract this 2 cotan x over to the other side of the equation. So we'll move it over. So as we do that, that sets it equal to 0. So our equation would now read the cotan of x times cosine squared x minus 2 cotan x equal to 0. So there's step 1, setting equal to 0. And now, if I look at this equation, what do we have? We have a common factor. So now, step 2 is I want to factor, right? I have a GCF, a greatest common factor of cotan x. So let's go ahead and factor that out and see where that leads us. So as we factor out the cotangent function, so as we bring out that common factor that's showing up in both terms, right? If we bring out cotan x, we're left with, in the first term, a cosine squared x. And our second term, we've taken out cotan, so we're left with minus 2. And it's equal to 0. So now we've got a factorization. And since we have a factorization, we can now apply our 0 factor property. So we know if this product's going to equal 0, then one of these factors, right, is going to have to equal 0. So let's go ahead and apply that. So using, again, more algebra review in this trig equation. So that implies cotan x can equal 0, or cosine squared x minus 2 can equal 0. Well, when does cotangent equal 0? So if you take that first equation, now cotangent, remember, to find, if you want to think back to your unit circle approach, that's x coordinate over y coordinate. So on the unit circle, let's write that down. When do you have, all right, think about it. We want it to equal 0. That means the x coordinate's going to have to equal 0. Well, the x coordinate is 0 when you're at your pi over 2 marks. So, for example, pi over 2, what's the ordered pair? 0, 1. There's your x coordinate and your y coordinate. which implies if we took the cotangent of pi over 2, we get 0 divided by 1, which 0 divided by 1 is 0. There's a solution. All right, so there's one answer. Pi over 2 will be a solution. Right? Or you could look at 3 pi over 2. 3 pi over 2. Now remember, this is in the restricted set. Now remember, we got to look between 0 and 2 pi for solutions. So this will be the only other number, or only other radian measure. All right? Or if you're in degrees, it would be 270. Didn't specify, I'm going to leave it in radians. But we have an ordered pair of 0, -1. So there's your x and your y coordinate. So that implies the cotangent of 3 pi over 2 radians is equal to 0 divided by -1, which is 0. So that implies we have two solutions for cotangent being 0. In the interval between 0 and 2 pi, we have two different real numbers, pi over 2 or 3 pi over 2. There's solutions. Now that takes care of that factor. Now we also have another factor. We also have cosine squared x minus 2 equals 0. So what happens on it? All right, well with that one, let's go ahead and solve it. So that implies what? We need to go ahead and move the 2 over. Go ahead and add it to the other side. So cosine squared x equals 2. And then we could take the square root, right? Now remember with square roots, be plus or minus. So as we simplify down, we have the square root of cosine squared x, which is cosine x, what we're looking for, plus or minus square root of 2. Now with cosine, right, you're looking at x coordinates. Well, we're never going to have an x coordinate greater than 1. Square root of 2, what? 1.414 approximately? Well, this can't happen, all right? Outside our range, all right? So this is outside the range of cosine. All right, the range of cosine, range of your cosine function, just like sine is -1 to 1. So again, never going to happen. Never going to happen. We'll never have a cosine value of square root of 2, right? So cosine can't equal square root of 2, so this is undefined. So there is no value going to satisfy that. Now we had square root of 2 over 2, that's a whole different story, right? Pi over 4 would be a solution, right? Or if we want a negative square root of 2 over 2, right? We could look at, for example, 3 pi over 4. Right, and we can go to quadrant 3 and we can find a solution. But it's not square root of 2 over 2, it's square root of 2. Cosine never going to equal square root of 2. So again, as you look at that, there are no solutions to that. And if you were checking it, right, if you went to your TI calculator real quick, pull up your calculator again. Now if you go to second cosine, and let's type in the square root of 2. All right, and let's hit the enter button. Not a number, it says invalid, in error, domain, dimension, range. It's not in there. You'll see an error message. Can't get it. So again, you can always check with your calculator if you need to. But for that example, that means of those two factors, the only one we produce solutions from, real number values, right, are pi over 2 and 3 pi over 2 and cotangent. So those are the only solutions for this equation. All right, so let's go ahead and look at another one. So again, there are only solutions. We couldn't get any from the other factor. Now looking at example B. At example B, let's do the same thing. Now we want to solve this equation. Well, my first step, let's go ahead and step 1, let's set it equal to 0. So I'm going to go ahead and move that 1 over to the other side of the equation. So let's go ahead and subtract the 1 over. And as we do that, what do we have in our equation? So that implies 2 sine squared x minus sine x minus 1 equals 0. Now when I look at that like I do a quadratic equation. If you took out the sine function, that would read as 2x squared minus x minus 1 equals 0, right? If you're looking at it as a quadratic. All right. Well, what I want to do, factor. So now that we've set it equal 0, let's go ahead and factor. All right. So again, think of it like a quadratic. I'll make that a note. Factor the quadratic trinomial. So with that, let's go ahead and break it down. And every quadratic has 2 linear factors of x, and we're dealing with a quadratic trinomial. You can find these 2 linear binomial factors. But for example, we want a 2 sine squared x. We're going to need up front a 2 sine x and a sine x. Right? If you multiply those together, you would get 2 sine squared x. And of course, 1, as we're looking at the factors of 1, right? Of course, the prime number, its only factors are 1 in itself. So we'll need a 1 and a 1 here at the end. Now we need that to be negative, so one of them has to be a positive, the other's going to have to be a negative. But the key is our middle term. Our middle term is a negative sine x. So that means we want to put the minus with the larger of the 2 products. So the minus is going to have to go here on the outside and our plus on the inside, right? So if you were to check these, that product is negative 2 sine x, and this inside product is sine x, and they add up negative x. So yeah, if you distribute that, or think of it like a quadratic trinomial, full it out, right, you get 2 sine squared x minus sine x minus 1 back. So we factored that quadratic, for so to speak, even though it's not a quadratic. All right, so again, think of it as a quadratic. So using quadratic properties. Now with that, we're ready to go to our 0 factor property. So that's going to be our third step. Third step, let's apply the 0 factor property. Now that we have a factorization, we know for this product to equal 0, that means that one of my factors going to have to be 0. So we set each factor equals 0. So 2 sine x plus 1 can equal 0. Or sine x minus 1 can equal 0. Right? And with that, we need to go ahead and solve for x. Let's go ahead and do that. Let's go ahead and get x by itself. So again, we'll solve for x in both of these. Make that note. All right, so there's our x terms. We'll get them by itself. So we'll go ahead and subtract that 1. We'll work on this one too. Add the 1 over. So subtract the 1 on both sides. Add a 1 to both sides. And as we do that, what do our equations now read? Now we've got 2 sine x equal to negative 1. And over here we have the sine of x equaling positive 1. And let's go ahead and finish out this first equation here, this first factor. As we divide out the 2 on both sides, we get what we're looking for. We finally get the sine x term isolated. And now you should be able to tell me your solutions, and you don't need a calculator. Remember, sine's evaluated by the y-coordinate, right? So we're looking at y-coordinate values to be negative 1/2. And somebody tell me on the unit circle, when do we have a y-coordinate to be negative 1/2? Right? Well, we're going to be in quadrants 3 and 4 at our 30-degree marks. So think about your unit circle. So if you need to, you can write it up here. On the unit circle, if you look at, for example, the 30-degree mark in quad 3, 180 plus 30, which is 210, or pi plus pi over 6, which is what? 7 pi over 6. So 7 pi over 6, if you're looking at it in radians, that ordered pair would be what? Square root of 3 over 2? Well, it would be negative square root of 2 in quad 3, and a negative 1/2. But there it is. There's that y-coordinate. So yeah, sine, right? There's the y-coordinate. So that implies x can equal 7 pi over 6. And that's between 0 and 2 pi. I don't have to add it. I don't want to add any multiples of 2 pi. That's one thing I want to make note of is different in these problems. Why aren't we adding or subtracting multiples of 2 pi? Because we got to be within the interval of 0 to 2 pi. Anytime we add or subtract multiple 2 pi, that would get us outside of that restricted range of values for x. Now we also have on the unit circle, you could also look at 11 pi over 6. At 11 pi over 6 on the unit circle, right, and I can write that in here if you need to. 11 pi over 6, we have a ordered pair of square root of 3 over 2, negative 1/2. So there's that negative coordinate. But there's two solutions already for this equation. Now, it's just looking at the first factor. We also have this other factor. So let's go ahead and look at this one over here. And if you want, we can put it different color. So how about sine of x equaling 1? Well, again, we want a y coordinate to be 1. So if you're thinking about your unit circle, when do you have a y coordinate to be 1? When you're looking between 0 and 2 pi, at pi over 2. At pi over 2, our ordered pair is 0, 1. There's that y coordinate of 1. So again, as we're looking at our value, there's a solution. So that implies x would need to equal pi over 2, because sine of pi over 2 is 1. All right? So there's a solution. So altogether, in the end, we have 3 solutions, right, to this equation. So if you want, we can put them all together. Just going to move that over here just to separate these. So yeah, altogether we have x equaling what? And I'll put them in order. Smallest to largest, pi over 2, 7 pi over 6, and 11 pi over 6. There are 3 solutions. All right. And we got one more. Let's move on to our third example here. So moving on in, I'll go to another page, give us some room. So let's solve this next one. I like this next one just because it does a little identity review. Got sine of 2x. So with that, we're going to have to apply the double angle identity for sine. Also have cosine 2x, which means we're going to have to apply the double angle identity for cosine, equal negative cosine x. So my first step, I'm trying to solve x, right? That's my goal. What does x equal? And again, we are restricted between 0 and 2 pi. With that said, we need to apply the double angle identities. All right, that's going to be step 1. We'll write that down. Apply double angle identities. Now again, we should know these, not look back at your identities. We know sine of 2x, for example. Sine of 2x, right, is equal to 2 sine x, cosine x. And just like cosine of 2x, it's equal to cosine squared minus sine squared. So let's apply those. So that implies we have 2 sine x. So we replace sine of 2x, what it equals. There's the identity. Times the sine of x minus cosine 2x. So let's go ahead and replace it, what it equals. And we know that's cosine squared x minus sine squared x equal to negative cosine x. So now we've got everything, and I just forgot one thing. Be careful. I just forgot to bring down my cosine x. Right, it's being multiplied with cosine 2x. All right, but now we've got everything written in terms of x. So that was what we need to do at the beginning. We need to go ahead and get rid of double angle. We got to get rid of x, so we want to solve for x. Now, with that said, right, our next step, right, what are we going to be doing in the next step here? All right, we want to go ahead and distribute, right? Go ahead and distribute through here. Let's multiply. All right, distributive property. So let's go ahead and clear out parentheses. Now, as we multiply, we have sine x times 2 sine x cosine x. So we're going to take that sine x and multiply it through. Well, that would be 2 times sine x times cosine x times sine x minus, so there's the sine x distributed. And then we got the cosine. Now there's 2 different terms here, so you do have to be careful. We have cosine squared x times the cosine x that we distributed minus sine squared x times the cosine x that we distributed equal to negative cosine x. Well, sine times sine. Let's go ahead and simplify where we can. We know that sine multiply with sine makes sine squared. So we end up with 2 sine squared x cosine x minus, and here as we multiply, right, we got cosine squared with cosine. So they multiply together to give us cosine cubed x minus sine squared x cosine x. All right. And what I want to go ahead and do, I want to go ahead and set this equal to 0. So let's go ahead and do that. Let's go ahead and move this term over. Let's go ahead and add that cosine x over. So again, I want to set it equal to 0 also. So as we do that, what do we have as we set this equal to 0? What do we have as a common factor? All right, what's showing up in all these terms in this example? We got a cosine x, right? Cosine x, cosine x, cosine x. So we have a GCF. Let's begin to factor. So again, now if you want, before we do that, it might be a little easier. Let's don't factor yet. Hopefully you recognized we do have some like terms, right? And if you want, let's just go ahead and add those up. We don't need to factor yet. Let's simplify things. So yeah, we have some like terms here. So let's go ahead and add those together. So we have all together what? Sine squared x, cosine x, 2 sine squared minus sine squared. So as we combine the like terms, as we simplify down, and let's go ahead and put that in black, I've got sine squared x, right, cosine x. So we multiply, add those together, they're like terms, that's what they equal, minus the cosine cubed x plus the cosine x equals 0. And now I'll factor. So where we want to factor, so let's find that GCF. So GCF, greatest common factor, is cosine x. And as we go ahead and do that, as we factor out the cosine, all right, what do we get? So we're left with, in this first term, a sine squared x. We're left with, in this second term, a minus cosine squared x. And then we're left with a, what? Plus cosine x. That'll be plus 1 as we factor out the cosine. And does anybody notice, what do we get inside here? What is 1 minus cosine squared? Right? We're getting ready to look at what? Pythagorean. So here's my Pythagorean identity. Simplify. Pythagorean identity showing up. Our fundamental identity in trig, right? We know that sine squared x plus cosine squared x equal 1. So yeah, if I was asking you to solve for sine squared, we subtract that over. Sine squared x equal to 1 minus cosine squared x. There's the identity. So we can replace that. So that's equal to sine squared x. So as we're simplifying down, it's simplifying nicely. We factored out the GCF cosine. And then what was left, we were able to simplify a little further. This is equal to sine squared x plus sine squared x. So we have 2 of them equal to 0. So cosine x times sine cubed, or I shouldn't say sine cubed, 2 sine squared x. As we add those 2 terms together, equals 0. And now we apply the 0 factor property. So applying the 0 factor property, right, that implies cosine of x can equal 0, or 2 sine squared x can equal 0. So again, apply 0 factor. We'll make that note. Now, we again should be able to easily solve by hand. Shouldn't need a calculator. When does cosine x, remember we want x coordinate. Think about your unit circle. So when is the x coordinate 0? X coordinate 0 when you're sitting on what? Pi over 2, 3 pi over 2. There's two solutions. Pi over 2, 3 pi over 2. We have a cosine value of 0. And how about over here? Now, we got a little bit of work to do. We divide out our 2 on both sides. As we do that, we get sine squared x equal to 0. And then you can take the square root, right? If you take the square root of both sides, and it doesn't matter if it's plus or minus, we're dealing with square root of 0 to 0. We get sine x equals 0. Now remember, sine holds the value 0. We're looking at y coordinates. So when is the y coordinate 0? At 0, pi. Now we don't want to include 2 pi. 2 pi, remember, look back at our restrictions on x. It must be less than 2 pi. So altogether, we have 4 different solutions for this equation. So that implies x can equal 0, right? Pi over 2, pi, and a 3 pi over 2. So there are 4 solutions to our equation in the end. So I hope that helps you in solving algebraically. There's some good examples. I like that one just because it reviews a little bit with our identities. We had to apply our double angle identities. We had to do some algebra. We had to combine some like terms. We had to factor. I do have some worked out graphically with your calculator in your notes that you can look at using the intersection method, graphing the 2 sides, showing the equal. And I'll let you read through those. If you need any further examples or help, I'll be glad to look at it. Just let me know. So we'll stop there with our lecture for 7.5 and solving these trig equations.